Imagine waking up one morning and discovering that your GPS doesn't work, satellites are malfunctioning, radio communications are failing, and the cause is not on Earth. It's a storm coming from the sun. Because the space around our planet is not empty. It is filled with a vast ocean of charged particles, plasma, constantly flowing from our star. What if I told you that Earth is sailing through that invisible ocean every second of every day? A stream of solar wind moving at more than 1 million kilometers per hour. Most of the time, our planet's magnetic field shields us from it. But when the sun erupts, releasing massive clouds of plasma, called coronal mass ejections, that protective shield is suddenly put to the test. These solar storms can disrupt satellites, interfere with navigation systems, threaten astronauts in space, and even affect power grids here on Earth. Understanding that invisible environment, what scientists call space weather, has become essential for protecting the technology our civilization depends on. Welcome to Highway to Space. I'm Dan Profir, and today my guest is Dr. Luca Sorriso-Valvo, a plasma physicist studying the turbulent solar wind and the complex interactions between the Sun and Earth. His research helps us understand how space weather works and how humanity can better prepare for the storms of our own star. Luca, welcome to the show.
Hi. Thank you very much for inviting me. It's a pleasure to be here.
You choose to specialize in plasma physics rather than studying distant stars. What drew you toward exploring the space environment closer to Earth instead of looking further out into the universe?
That's a very good question. It's a bit of a mix of luck, just sheer causality, and some inspiration that I got along the way while I was studying. So I think everything started when I was a kid, a school kid at maybe in the mid 80s. I was going to the beach in the Mediterranean, and I remember spending some nights up in my apartment roof looking at the stars, and I say, okay, I want to study that stuff, the stars up there. This is how I started. But then when I enrolled in my hometown university, I find out that the matters they were studying in that university was specifically space and the sun maybe, and the near Earth space, not really the faraway stars. And it was a bit too late to change. But actually, I was absolutely in love with it since I started taking my courses. So that happened at the university at my master level when I was starting studying the physics of plasmas that make the solar system, that compose the solar system. And I found it extremely, let's say, more concrete than just the faraway stars. Even there was a winning thing is that for space, nearby space, we have access to measurements from spacecraft that can be directly there and measure the material they are embedded in. But for faraway stars, we only have some light coming from there. We need to interpret everything. So I think I started passing from a more, let's say, observational appeal of the stars to a more how do you say, inquisitive and quantitative study with equations and numbers of the closer material, which is the space around us. That's probably what drove my switch. Maybe not so romantic, but that's it.
For those of us who haven't thought about plasma since high school physics, myself included, what exactly is plasma? And why is it so dominant in space?
So plasma is usually referred to as the fourth state of the matter. After, solid, gas, liquid, and then there is plasma, which is similar to gas, except the particles that compose it, the atoms that compose it are no longer atoms, they are fully ionized. So they split into electrons and nuclei, which can be protons or even more, let's say, heavier ions and nuclei. So in some sense, all the atoms are split, and this means that there are charged particles. This makes a big difference with the normal gases where particles are neutral, except for maybe some which is getting some electrostatic charge. But in the plasma, all the particles, or let's say majority of the particles that control the motion, are ionized, which means are charged. This makes it interact with electromagnetic fields because we know from Maxwell equations and from the physics that charged particles will interact with electromagnetic fields. And so this makes it way more complex than a gas. And I think the properties, let's say the conditions to achieve this state are quite specific. And you need the particles to be very hot and very rarefied. And by hot means that they have a lot of energy, they run very quickly. And by rarefied means they don't hit each other very often, in which case they might recombine as neutral atoms. But if there are not so many of them, they might just not never hit another one and don't recombine. Or if they're hot enough, even if they hit each other, they're so fast that they don't get the energy to recombine. They just collide and scatter each other like a pool table balls. So this is more or less the conditions that you need to achieve. And this is why it's so rare to have them on ground, on planet Earth, because we don't have those conditions. Here, all the gases are highly dense. The density is usually like 10 to the 23 particles per centimeter cube, while in space, we're talking about a few particles per centimeter cube. It's a huge difference in density. And also temperature are not so great. So I think the only way you can get it on Earth is, for example, in lightnings, in the channels where lightning happens, the temperature gets so high for a split second, for a tiny moment, but during that tiny moment, that it's a plasma channel that transmits the current, or maybe some very hot flames, which are not natural though, they are human created. So there's not so much of a natural plasma on Earth, on the, let's say, below the atmosphere.
Just to clarify something, the flame of a candle isn't actually plasma, is that correct?
A normal flame at low temperature is just very hot gas, not really plasma, which means that the atoms are very hot, they are full of energy, the electrons want to go away, but they don't do it, they still bound to the atoms. When the temperature reaches very high temperature, the electrons become so fast around the atom in a very classical view of the atom model, then they can get rid and they can escape, let's say, the attraction from the proton, and they can ionize, and that becomes a plasma. But for this, you need very high temperatures, which are not very easy to find in natural flames. But if you have like industrial grade flames, that you can get that temperatures.
Would it be fair to describe plasma in space as something like an electric ocean?
I might say electromagnetic, maybe ocean, because you need magnetic field. It's a crucial, very important element of it. And there is no plasma without a magnetic field, because just the motion of the particle will create a magnetic field itself. So yes, in a way, it can be an electromagnetic ocean. You can think about that, very rarefied, but if you look it from far away, from taking the distance and look very big things, they move a little bit like a gas or like a fluid. I think there's actually laboratories on Earth that try to reproduce similar conditions as a plasma, and one of the most used is liquid metals. So there is a liquefied metal, usually it's gallium or some other very heavy metal, um, that are stirred and they move and they can simulate a fluid. And because they are metals, they are conductors, so electrons can flow on them freely, like they will do in a plasma. So it's the closest thing that we have for simulating a plasma. We can also make plasmas, but if we want to mimic plasmas, I think a liquid metal is a nice example of that.
Earlier you mentioned that plasma behaves more actively above Earth than it does here on the ground. Could you expand on that a bit? What makes it different?
So once again, on Earth, when we can create plasmas, we have those very, naturally occurring plasmas are very confined to small regions. They last for very few seconds, if not less, and they don't really survive a long time. So there is some interesting dynamics there, but if you go up in space, things are so different that in space you need to imagine the scale of it. We're talking about very large scale, like huge distances and huge, let's say, scale, dimension of the structures that we consider. And also we need to think that the plasma there is really rarefied, so it can freely move as a liquid, as an ocean, as you were mentioning, creating waves, creating turbulence, and a lot of dynamics. It's actually even more complex than that, because at a difference with the normal neutral gases that we are used to on Earth, they are so rarefied there that we need to consider even a more advanced level of, let's call it statistical mechanics. So, which means that the laws that regulate the particles are different from terrestrial gas. So there is a whole world of phenomena that can occur into those plasmas, starting from fluid phenomena down to phenomena related to the particles interacting directly with the magnetic field in electromagnetic fields. So it's a really a huge variety of dynamical processes, but most of them can be really explosive, I will say, also powerful, explosive, carry a lot of energy, and so they are interesting for us to study, both from the astrophysical point of view, then from the applied point of view.
Let me return to that point for a moment. When you say plasma above Earth is more active than on Earth, what exactly does that mean in physical terms?
Yeah, this is very, very true. And I think recently we had a lot of exposure to this point in media, for example, because we have a lot of very beautiful images of the sun that propose all the features that happen, like explosions and things like that. So the sun is not quiet at all. It's very dynamical. It has a large time scale variability, which is around 10, 11 years, which is a solar cycle, in which the activity of the sun goes up and down from a minimum quantity of very minimal or nearly no specific magnetic activity to a very peak of maximum activity. And this is the very well-known 11-year cycle of the sun, related to the emergence of sunspots, for example. And that cycle, within that cycle, there are the small, let's call them events, like explosions or emergence of sunspots with all the magnetic field that they carry together. And so this is, each single event is an amazing let's say, collection of processes, of physical processes of different kinds that we want to study because we want to understand how it works. But it's absolutely, and it can go from something very steady, very quiet, to something very explosive and with all different variety of energies involved. So it is highly active, and this activity is modulated in time. It goes from some minimal to maximal, but it's always active anyway, I would say.
That's fascinating. Let's shift our focus now to the sun itself. Although we often think of the sun as a steady source of light and heat, it's actually an extremely dynamic and sometimes violent environment. Could you explain what is really happening there?
This is one of the products of the solar activity. When there is an explosion, well, we call it explosion a bit improperly. We call it properly a solar flare, like this emission of energy that is associated to some very peculiar phenomenon called magnetic reconnection that occurs in the atmosphere of the sun, so in the layers very close to the surface of the sun. sometimes those let's call them explosions, they produce a blob of matter being spit out in space. And so let me start by saying that the sun is always emitting some particles that escape the gravity of the sun because they are so hot and they fill the space. This is a continuously flowing material from the sun into the solar system, and it's called the solar wind. Now, in the specific event of solar flares, inside this solar wind, there is also a supplementary expulsion of an explosive bubble of material that is spit out, and it blows inside this solar wind, but it's usually faster than the solar wind, so it expands faster, and that's called a coronal mass ejection, CME, which is produced during at flares, and then it expands and invades the solar system. Just to give the scale of these objects, when they reach the Earth, their size is might be of the order of 10, like, let's call it probably a fraction of the distance from the Earth to the Sun. So it's a really huge object, like 100 or more times the size of the Earth. So these are really huge objects flying up in space. So they often hit the Earth, by the way.
Are these processes continuous, or do they occur more as sudden explosive events?
So both exist. So the CMEs are explosive events. They are very sporadic. There are not so many around. Once in a while, there is one, and you hear about it oftentimes. But this is, as I was saying, overlapping to a continuous flow, which is the solar wind. The solar wind is always there. There's no stopping solar wind. It's always continuously flowing. It can be faster and slower. Like the solar activity is modulated and there's a lot of variability, even the solar wind can be faster and slower, but it's always there. It's like an atmospheric wind, I would say. There is a stronger wind, a slower wind, and maybe some more turbulent wind and some less turbulent wind, but it's always there, like in the atmosphere. And then once in a while, you have those explosive events that boom, overlaps it. So yes, it's a combination of the two.
As I listen to you, it occurs to me that this topic might sound quite abstract or distant to many people, but in reality, these phenomena can have very real consequences for life and technology here on Earth, can't they?
This has to be looked at in an historical perspective, maybe. I think until we started having electromagnetically working tools, like things based on electricity, basically, there was not so much of an evidence of this activity, except for one, which is the auroras, the northern lights. These are probably the major evidence that we have that the sun connects to the Earth. Now we know that whenever there is an explosion on the sun and the blob, this coronal mass ejection, is sent in the direction of the Earth, then this squeezes a little bit the Earth magnetosphere, which is the magnetic field of the Earth that surrounds the planet and protects from cosmic radiation and things like that. This is squeezed a bit, and there is a chain of events that lead to the generation of the auroras. So the auroras are generated by solar storms that propagate to the Earth and create what's called a geomagnetic storm. And the more visible effect of that is the auroras. There are other ones, though, which are less visible and more subtle that we know about since we started using electricity. And these are effects such as, so in general, what happens is that the magnetic field of the Earth fluctuates strongly instead of being steady as usually is. And those fluctuations, magnetic field fluctuations, generate currents. And there is all a system of fields and currents that develop. And so there is perturbations in the magnetic field and currents on Earth. This means, for example, if you have a power grid where you carry current, electrical current for electricity, for your turning the light on, that power grid, if you have this magnetic fluctuations, there might be some fluctuations in the current as well. So the current can spike, for example, spike up, become more intense because of those contribution from the sun. And that might, for example, burn transformers at the power grid stations or in your houses. So it's it's happened before several times actually that there were that kind of incidents where a solar storm has driven disruption in power lines, for example, because of those induced current generated by the storm. That's another example, I will say.
Let's step back for a moment and talk about the aurora phenomenon. We usually associate auroras with regions near the North Pole or South Pole. Why do they appear primarily in those areas?
Yeah, so there is two levels of answer here. The first level is the auroras happen at the poles. That's where the magnetic field of the Earth is it's going out, and because auroras are generated by particles that are shot into the Earth, and because they are charged, they have to follow the magnetic field. So they if wherever they come from, they will finally end up on the Earth on the poles where the magnetic field of the Earth comes out, let's say. But this is why they are in the northern regions usually, but also in the southern regions with exactly the same frequency. The difference is that regions in the southern hemisphere are way less populated. The populated areas of the southern hemisphere start at very much lower latitude, closer to the equator, which means that there's no enough people close to the pole to see them. Otherwise, they are both in both hemispheres nearly equally. But yeah, there is a preference for high latitude and poles. When they are really strong, then they expand so much that can be seen even at lower latitude. That was the case, I think, in the last couple of years. We had a few events like that that were visible in the Mediterranean or in much lower latitude, in lower southern England, sometimes even in Greece. Those are connected to much stronger events.
Yes, I remember one event a couple of years ago in the United Kingdom, even in southern England, which was quite unusual. So the aurora was faint but still visible. Events like that really capture public attention.
We have an answer because we do have planets without a magnetic field on the solar system, in the solar system. So we can look at those and deduce what's happening when you don't have that. An example is Mars. Mars is a planet with, you know that the magnetic field of the Earth is generated by the motions of the liquid core, iron core of the Earth, which makes like a dynamo, like the one you have on your bike to generate the electrical light. And so this motions generates this, let's say, supports this magnetic field that keeps it there. But if the planet cools down and the iron core stops its motion, like it happened on Mars, then the magnetic field slowly fades down, it's consumed, and then at some point it disappears. So Mars has a very weak magnetic field, very faint, and basically all the magnetic field is inside the planet. It doesn't even reach outside of it except for a few spots. So what we know is that once you remove that shield, magnetic shield that protects against the solar wind, again, because solar wind is made of charged particles impact a magnetic field. They cannot cross the magnetic field. They will have to go around the magnetic field. And so that's what happens with the Earth. They go around the magnetic field and they don't hit the Earth. The solar particles don't reach the Earth. They are separated and protected by the shield, which is the magnetic field. If you remove that, the solar particle will reach the planet, as they did with Mars. And the first effect over very long, billion of year probably scale, it will strip little by little all the atoms from the atmosphere just by hitting the atoms and stripping them away, carrying them away into space. So the atmosphere might be lost if the planet had one to start with. So first long-term effect, most striking probably, is the planet will lose the atmosphere. Then there is a short-term effect. Imagine you switch down the Earth magnetic field suddenly like that, immediately. As we saw in movies, what happens is that radiation from the sun, those particles from the sun, can penetrate and reach the surface. And so we become exposed to radiation. So anything that we know is very harmful for human health will happen. And then I think it's a good driver for mass extinction, and which probably happened in the past.
Moments like that remind us how fragile our protective atmosphere really is. We tend to take it for granted. We breathe the air, we live under this shield, but in reality, it's constantly protecting us from a very hostile environment.
Unless we have time to evolve, to adapt to it, we might not survive to it. I don't exclude that in some other planets, there might be some form of life which we don't even think about as a possibility for form of life that is adapted to live, to coexist, or even to feed on the radiation. So it's we don't know. It's a possibility. I wouldn't exclude it. So energetic particles carry energy. What we know is that life to exist needs energy. And if you can harvest radiation for that, then you might still be alive with radiation. But you need time to adapt or maybe to evolve that way. Yeah.
Let me challenge you with a broader question now. How vulnerable is modern civilization to solar storms and solar wind events? Our technological systems seem incredibly advanced, but are they also increasingly exposed?
So this is, I think, the first time that we mentioned space weather tonight, and that's mostly probably the most important point of the whole show today. I think space weather is a really important discipline that is developing recently, because only recently we are understanding how exposed we are to what we can call space weather risk. So I will say that human health is not really concerned, or at least there's no proof of that at the moment, except for people up high in space, for example, astronauts, but even maybe aircraft crews or people on board of aircraft when they cross the poles where they are more exposed to radiation. There are some evidences of health effects on those people, of course. But other than that, on Earth, we are weakly affected by that. Some animals are more affected than us. For example, those that rely on magnetic fields to orientate. Like there's a lot of birds that do that, or bees, or some dolphins, some cetáceos. They do orientate using the whales as well. They navigate using a natural GPS, which is like magnetic field, like a compass that they have in their own bodies. And those are affected by storms. We have seen before like events of whales, how do you say, when they go on a beach and they say they're stranded, uh, yeah, on beaches because they lost orientation due to solar storms. But this is for the animal kingdom. We humans, we don't have a lot of sensitivity to the magnetic field, but our technology does. So there's a whole lot of technology that are usually affected by storms and potentially affected by very severe storm that we haven't experienced in the last maybe decades, but they are still possible. For example, I'm thinking about, as I said before, power grid disruption, but also blackouts in communications, like radio communication between Earth and space, or across Earth using, when they use the ionosphere as a reflecting tool. GPS communication can be affected. So all the positioning system from aircraft, boats, or everything else can be severely affected. Everything that has to do with satellite communication, so internet, think about all the possibility that rely on space satellites up in space can be disrupted, and all the spacecraft in space are exposed to risk, of course. So we could lose easily tens of thousands of satellites if there is a sufficiently big, strong event in space. So if you do all the math, I think that there's a recent estimate that one event which is similar to the biggest event we know so far, which is an event that happened in 1859, I think. That's called the Carrington event. That sparked auroras all the way to the equator. An event like that would create damage estimated in the order of a few $1 trillion. So we're talking about like very huge damage potentially to the human infrastructure, I would say. Not really health, not directly at least, but definitely the infrastructure.
In many ways, despite our technological progress, we remain surprisingly fragile, don't we?
Well, this is like when you build you build a skyscraper and then you have an earthquake, right? So if you build a skyscraper, it might be affected by the earthquake. If you don't, if you sleep under a tree, nothing will affect you. So yes, in a way, we are building advanced technology that is fragile to some aspects. The point is this aspect was not so, and still not completely completely sufficiently considered, and there's still an underestimate of the dangers into that. Some governments, not all governments, some governments are starting finally looking into this, but it's not a very common thing yet.
A good reminder of how connected we still are to our cosmic environment. Now, there's another fascinating aspect of your work I would like to touch base with. In addition to your research, you are involved in training astronauts for the European Space Agency. What does that work involve?
So there are two levels at which they need to be, let's say, the astronauts need to be conscious or trained in this field. One is because they need to know the potential risks. And so they need to be aware that if something like that happens, if there is an alert, what are the potential consequences of them? And the very simple example is if there is a solar storm and an astronaut is doing his repairs outside of the International Space Station, he has to run back inside and hide into what's called, I don't remember the name, but it's a safe module in the station, which has specifically thick walls to protect against radiation. So if they don't, they might be exposed to radiation, which would be similar to getting into Chernobyl reactors after the disaster. So I think this is one thing. The second thing actually are three levels. The second level is that they need to know the science, at least basics of it, because astronauts oftentimes run experiments on the space station. And some of those experiments might have to do with plasma physics or radiation or space weather. So they need to be able to more or less at least grasp the meaning of what they're doing if they want to do it right. And there is a third level, which is mediatic, I would say. An astronaut must be able to must know those things because they cannot just go on your interview and be asked something, then say, oh no, I don't know about space weather. What is it? They need to know. So they need to be educated in those things. It's part of their, let's say, skill set that they need to have. So those three levels all make for necessity of training in this subjects.
Luca, are future missions to the Moon or Mars more exposed to radiation hazards than missions in low Earth orbit?
Well, yes, very much actually. As I say, the terrestrial magnetic field is a shield. The astronauts, the ISS, are well inside this shield. So they are screened. So only the strong radiation come in. The moon, on the other hand, is most of the time inside this shield, but sometimes so a part of the orbit is outside of it. So at least for that part of the orbit around the Earth, they get exposed. It gets exposed to solar radiation directly. It's actually near the border, so it's sometimes it gets in, sometimes it gets out, depending on the position of the terrestrial magnetic field. Mars, it's a completely different story. Mars is fully exposed, so it gets even more radiation. The distance is much larger, so there is less radiation intrinsically because it's expanding, so it's diluting as it expands, but it's still all there. There's no shield. And so if we want to be on Mars, we need to think about systems to protect from radiation, artificial system to protect from radiation. Someone was speaking about creating a small local artificial magnetic field to screen, and that might be enough or not, we don't know. So it's under study. But yes, so there is a way more risk. So I think even, let's call it buildings or spacecraft must be more resistant to radiation.
How would you compare the radiation environment on Mars with that on the Moon, for instance, considering that the Moon lacks both a substantial atmosphere and a global magnetic field?
Yeah, on Mars neither, don't forget. But yeah, I think I don't know the numbers. Someone should do the math and check if the dilution with distance compensates for the small screening from the magnetosphere at the moon. But I suspect in both cases it will be quite, let's say, exposed. I don't have an answer about the ratio of the two, but yeah, I would say both are strongly exposed. So you can predict what's going to happen at the given time in a given point. This you can predict. What's predictable are the global properties, statistical properties. So you know how much this quantity, so velocity or magnetic field, will be fluctuating during 1 hour. On average, we're going to have this level of fluctuations. And we're going to have this an estimate of a number of points where there is an excess of dissipation of that energy. It's a very complicated thing, but it's not predictable in any other way. And even that is driven by the sun, which is unpredictable itself. It's a solar activity. We know about the cycle, this 11-year cycle up and down, but we don't know about the fluctuations within the cycle. And those are also unpredictable. Everything is very chaotic. So we can only do some statistical analysis exactly like in the terrestrial atmosphere. So we know that there's going to be some big motion like that, but we don't know the details of it. We don't know exactly when and how it's going to rain. Well, in the atmosphere, we're getting better and better with that. In the solar wind, we need to study more to get to the same level, but it's still very early. And yeah, there is a lot of chaos, as you say, and unpredictability in the system. Yeah, absolutely. That's why what makes it very appealing to me. It's intrinsic complexity.
You also worked with Professor Giorgio Parisi. What does collaborating with a Nobel Prize level scientist teach you about how great science is actually done?
That's a very interesting question. So my experience with Giorgio Parisi was I was not working, let's say, doing a science project with him, but it was in the same team. So we were working in parallel, exchanging ideas and showing each other our results. So it was a sort of a light collaboration for a while. I think, and I met also another Nobel laureate when I was working in California. And that was the guy that got the Nobel Prize for inventing the laser, basically, in the 50s, late 50s, and was very old but still active. So every time I speak with those people, and when you interact with them on the science level, there are so many factors that makes it pop up. So it's a completely different human being. So I think the most striking thing is the speed of thought. So the speed at which they can process information and respond with some analysis result or things like that. It's extremely faster than anyone else that I ever seen. And also the ability to have a very global vision, uh, joining together things that normal people don't see as possible to join together. So making connections between things, it's very, very difficult. And also, again, always thinking ahead. Yeah, so but what is the next step then? And they're already on the following step while you're thinking of the next step. So it's also this. So it's speed. It's a breadth of thinking and the ability to advance thinking. Probably this is the let's say the amazing sides of it. There is one downside to it, which is it's not always easy to efficiently communicate with them because of this difference of speed. So it's like you need to synchronize to some frequency which is not your own, and then if you can feel overwhelmed by the and now what do I say now? I need a day for thinking about that before I can answer. Yeah, so it's
That sense of curiosity and playfulness seems to be what often separates good scientists from truly great ones, yes. But your mentor, for instance, Vincenzo Carbone, also played an important role in your career. What influence did he have in your scientific path?
well, it is quite important, and it can be important in either way, in a positive and negative way. I think most people I know have usually good experience with their mentors, and sometimes it's not. Sometimes it can be very bad, and this can shape the career of some of my colleagues. But in general, I would say that you need to think about it as something that can generate a school. And what by a school, I mean a group of people that explore the nature of things, the physics, for example, in a given way with a given concept, and try to understand if their idea is right. And then someone else somewhere else with a different mentor will have a different thing, different opinions. So this propagates in a way from a mentor to the let's call it pupils, and that what creates schools. But it's also, in a way, this is very nice, but it's also quite dangerous because it can limit the view of the researchers. So a researcher, to become a real independent one, needs at some point to disconnect from the mentor and to become independent and be able to contrast or to oppose the ideas of the mentor if he thinks it's necessary. So I think it can be dangerous to be too connected to its mentor, but it's a very good, of course, if you, I mean, it's a transmission of knowledge, and that it's always good in human nature. We progress like that. So it's the basis of progress, but it can be taken with care. Yeah.
What you're describing reminds me of a famous idea from one of the greatest artists in history, the Renaissance sculptor Michelangelo. When asked how he created his sculptures, he said that the figure was already inside the marble, and his task was simply to reveal it. In a way, science can feel similar. Nature already contains the answers, and scientists gradually uncover them. Would you agree with that analogy?
So this is a very tricky question. Research on fusion has started maybe now 50, no, 60 or 70 years ago. And every few years, there is a claim that, okay, we are closer now and we're going to have it in 30 years. But this has been said for at least 30 years. Since I remember studying this, it was always 30 years ahead, and now 30 years have elapsed and we're still 30 years away from it. So I think it's still very far away in time. Maybe it could be 30 years, could be fine, less, it could be more, I don't know. But we still don't have a clear idea when that could be happening to a commercially viable and useful energy. I have to say that to this, it doesn't help to have the press giving this, this flashy news every now and then. You get, oh, we are super close to solving the issue now because we reached this milestone, whatever. This is just a journalistic sensationalism, yeah, just to attract the reader. But no, it's actually quite damaging to the system because it makes you feel, oh, we are close, but then you never close, really. So no, not yet, not yet. Hold your horses for that.
Let's move now to another important topic, plasma and the future of energy. Many people immediately think about nuclear fusion when plasma is mentioned. How realistic is fusion as a future energy source?
So I think at this moment there is a lot of technical, industrial, even or medical applications for plasmas. There's definitely a lot of research in that, in what we call cold plasmas, which are in some conditions you can create a plasma which is not so hot, so you can use it for example, for medical things like to disinfect or operate or things like that. I'm not sure exactly what they do in medical plasmas, but I know that it's used. There is a quite recent line of research on that, and it's already been used in some experimental setups. It's used in agriculture and in waste treatment for, let's call it disinfection, but in general sanitation, maybe you can say, or protection against parasites and things like that, based on plasma. It's also used for technical, or let's say industrial, I think, processes such as deposition, metal deposition, or other kind of things like that. For example, to build semiconductors or other nanoparticles, whatever. I don't know, this is not my field, but I know that there is a lot of industrial application, and in space we are working on thrusters based on plasma. There are several projects that use plasma as a propellant, like the fuel for propulsion, and that could be a very viable and safe option, for a clean option propulsion in space. I think this is what I can think of, but yeah, there might be even more than that.
So in some areas, plasma technologies are actually cleaner and faster than conventional methods.
Depends on where. The faster is, I don't know, it depends on the system. In space, probably yes. It's usually, I think if I remember correctly, it provides a slow acceleration, but for a longer time. So you can reach eventually very high speed, but it takes a long time to reach it. But again, these are all prototypal, and I don't think there's anything running on plasma thruster right now, but there are experiments studying the possibility for industrial applications.
Luca, I'd like to finish with something that touches both the scientist and the person behind the scientist. You are the chair of Science Committee in Asgardia. How should space science influence future space governance?
This is a very good question, and my answer is basically what made me become a member of parliament of Asgardia, like enter this game, because I wanted the decisions made there to be science driven rather than politically driven. So I felt like, okay, maybe I can participate into that, and I think it's very important. We know that most of the human activities are driven by other things like power control and resources control, and I think space should be protected from that approach, which is not happening right now. We know that space is now probably the new place for a let's say Cold War, or we can call it a space race, but space race is not really for technological issues, but it's for military control, for commercial control, and everything else. So this is not going that way. I think instead we should be very careful because we don't know much about space, and whenever you play around with things you don't know, you end up burning yourself. So it will be very nice to leave it alone and study it for the moment until we understand how to use it properly. So I think my attempt in Asgardia as a chair of a science committee is to propose and promote legislation that will protect the environment in space, will protect humans in space, but also space from humans in a way. So yeah, I think it's an important task that I try to do whatever I can.
Yes, that raises an important point. Scientists and really all of us involved in space exploration carry a tremendous responsibility. As we expand our presence beyond Earth, we are not only advancing technology, we are also shaping how humanity behaves as a spacefaring civilization. If you enjoyed this episode of Highway to Space, make sure to subscribe, like and share, and join us as we explore the science culture and future of humanity beyond Earth. Until next time, stay curious about the cosmos and keep looking up.
Hey, space dreamers, this is Dan Profere, broadcasting live from Highway to Space. Inside, we're ready to ignite on a journey through the cosmos, star shining bright from the earth. on this highway